Thanks, Miloš, for the introduction. The talk is going to be about scalability of math for lexicography. The outline is basically going through the title. So first I'll talk about scalability, then about scalability of math, then about math for lexicography, and finally about scalability of math for lexicography. So first, what is scalability? Scalable tools or method works for different sizes, for very different sizes, for small, for big, and so on. Especially, we want a method which work for much bigger data, because we will talk about mainly processing or computing data. So the processing of much bigger data with the same method is the key theme of this talk. The scalability in real world does not work much. Usually, the real world is not scalable. You can usually handle 2 times more than what is expected, but usually not 10 times more. For example, when we have a small car which we use for driving 3 children to school, it's possible, if you are brave, to squeeze, say, 6 children into a small car, but you cannot squeeze 30 children in a small car. The same if you have a bus which can be used for 80 tourists. You can probably use it for 100 or 150 people, but you cannot use it for 800 tourists. So the real world is not scalable, and we know that it is not scalable, and we do not expect that it is scalable. There are from time to time some, for example, clauses which have labeled one size fits all, but usually this does not work. That it's not really for all. Yeah. So the real world is not scalable, and we should know that even the math or some algorithms are not scalable in computing. There is also, usually we talk about scalability when talking about more data or bigger counts or bigger sizes and so on. But the same situation is when we are going down. So if we have for example, bus, and we don't use it for transportation of just two children or to say personal driving. because it is not practical. We don't use some big screwdriver on a drill or something like that to repair watches, because it does not fit, it does not work. This is in the real world, it does not work, and we are going to see how it works in mathematics. Okay, so now the scalability of math. Basically, numbers have no limits. Numbers are scalable, somehow from the definition. But numbers are abstract things, and big numbers are hard to imagine. We usually have some idea what is 2 PCs and 10 PCs, but it is very hard to imagine, for example, 100 or 200 pieces without some counting. So if we have to estimate the size or the count, and we don't do the calculation, the estimations are quite poor, because it's hard. So in practice, we have to do some calculation to work with big numbers. So the first recommendation from me is don't estimate, but calculate. Here is some real example from February 2020. So it was before the pandemic, first pandemic wave. The Czech Minister of Health was asked whether Czech Republic is prepared for the pandemic, that whether we have enough masks, and the answer was that there are 25,000 of masks in stock and several more prepared in distribution. And it seems that it is a big number, 25,000. But when we do the calculation, we know that 50 masks are in one box, in one small box. And it means that 25,000 masks is only 500 boxes. And if we know that there are around 150 hospitals or main hospitals in Czech Republic, it means that the minister think that slightly more than 3 boxes per hospital is enough, and it is not obviously enough. But without the calculation, if we just see the number 25,000, we don't see the problem, because we don't we cannot imagine these numbers, we cannot compare these numbers, and so without this calculation, it's hard to do any decisions. Okay, numbers in computers are a bit different than the mathematical numbers. They have some limits. We have some limits in integer arithmetics. So the maximum is around 4 billions. In floating point 64-bit, it's 10 to 308, the maximum. So it is the number with say 308 zeros in the decimal writing. So it seems that it is a huge number, but we can easily come to these limits. And also there is limit on the smallest number. And for example, in computing some probabilities, it is quite easy to multiply many small numbers, and the result is 0, which is quite different in say probability, because 0 probabilities means that it is not possible. So we have to know about this limit when we do some computation, and work around these limits. But working around this limit is not so hard, and so I will not speak about these problems in the rest of the talk. Okay, so now about the mask for lexicography. We use the mask quite often, especially when we use some statistical methods. We do a lot of counting, computing some probabilities, different scores, and so on. So I will show some example about counts, about collocation scores, and about word embeddings, which is a bit different math, but it's used much more, and I think it will be used much more than in previous years. First, why the scalability is important. We use corpora as samples of language usage, and we somehow expect that bigger corpora are better samples because they are bigger. And so from bigger corpora, we can get more reliable results or better results. Usually we use some fine-tuning of method or some parameters and so on small data, and then using it on big data. And so we somehow expect that it will work in the same way, but if the method or algorithms are not scalable, then we can get bad results because of the different size of data. We also want to compare corpora or data of different sizes, and if some method or some algorithms get different numbers for different sizes, then we cannot use it for comparing corpora. And this is quite important. Also, the problems of scalability is in each part of the processing corpora or processing some language data, because everything in language, in natural language, is distributed using Zipf-ian distribution. It works for words, lemmata, multi-word elements, senses, and so on. And the Zipfian distribution mean that we have very different counts or sizes of some elements. So we have to know that the method works for both tens and millions and anything in between, because the different words have such different counts. And so if some method works for some small numbers, we can quite often use it for much bigger numbers, and that means that this scalability is very important in processing language data. There are two aspects of scalability. The first one I'll call usability, which means that we can compute the result in some reasonable time. What is reasonable? Sometimes it's just a few seconds. Sometimes it could be some batch processing. So even 1 week of computing is reasonable. But some algorithms are very slow for big inputs because of the quadratic time or some combinatorical combinations, meaning that the algorithms is very slow for big inputs. Sometimes changing the strategy of the algorithms or changing the algorithms can help. Sometimes some pre-processing or indexing could be used to speed up. So I will not talk about this usability, but I'll concentrate on usefulness, which from my point is that the result is useful or reliable. So we can use it in different situations, and we get the same meaning of the numbers and so on. Okay, so now the scalability of mass for lexicography. First, counts. Counts are the very basic of any statistics or any computation, and it is used in a more advanced method. And when we think about it, the counts are not scalable, obviously. When we have bigger corpus, we have bigger counts. If we have 2 times more data, we usually, in many situations, have 2 times bigger counts of words, lemmas, and so on. So the counts are not scalable. It is obvious, but we have to mind it and we have to remember it. Because in some methods we use only the abstract numbers, and we don't pay attention whether it is scalable or not, but it is important and we need the scalability. So the usual normalization is the division by the size of the data. So we have the relative frequency, then it is the relative frequency actually is the probability of words or other items. So there are some good features being its probability. So we know that the numbers are between 0 and 1, and the sum of all the probabilities are 1. So this is quite useful in many situations. But for say displaying some numbers to lexicographers or to human, usually we don't use probabilities because the probabilities are very small numbers. So we use something like hits per million, which has also quite good interpretation. So we understand what it means. Here is some. There is the first example. The following examples use the same structure, that on the x is the sample size in log scale. All these examples are from British National Corpus. So the largest sample size is the whole corpus, so it's 10 to 8, so 100 million, and while x is count or frequency depending on the display data. So the first part is just the counts, and the second part is the hits per million for word conference. Yeah, so we see that we get much bigger numbers for much bigger data for counts, and for hits per million it's from or for small samples the variance is quite big. We have numbers from, say, around 1 or something like that. So 1 hit per million up to about 220 hits per million. And for bigger samples, so when we start from say 5 or 6 millions, the variance is much smaller, and when we use bigger samples, so tens of here is the tens of millions, and almost the 100 million, the number of hits per million is stabilized around 60 or something like that. And this is actually the law of big numbers. So the more data is a better estimation, and much more data is much better estimation. So we use the counts are not scalable, and hits per million are scalable. We often use some reduced counts, for example, average reduced frequency, and and this is also the count. It is not scalable, and to use a scalable variation, we have do the normalization. So here I use ARF per million tokens, so it's similar to hits per million, and we can see that this is graphs for word language in British National Corpus. The first graph is for hits per million, and the second is for ARF per million. We can see that the numbers stabilize in different levels. So here it's around 180, and here it is about 45. And we can see that the variation of ARF per million is smaller for the same size. We can see that for tens of millions, the variance is much smaller than hits per million. So it's somehow normalize the reduced frequency, somehow normalize the counts. Here is example of average logarithmic distance. So it is another reduced frequency and document frequency, and both are normalized. Average logarithmic distance is normalized by using this per million, and relative frequency is normalized by number of documents. So it is sometimes called range. It is the percentage of documents in which the word occurs. So this is for word electronic, and we can see that the document or relative document frequency has bigger variance than the average logarithmic distance. Okay, so these are the reduced counts, and now collocations. Collocations can be computed using this algorithm. So we search the word in a corpus. It could be a word or anything else. We count words in the context and or in all context of all occurrences, and we compute some score. And there are many different scores using different approaches, from statistics from some information information theory and so on. And we display top results, so words with the top scores. Here are some examples for T-score and MI score for word break. We can see that T-scores highlights the most frequent words, and MI score highlights the low frequent words. In these listings, there were a threshold of 3, and we can see that many of the items are just on the threshold or a bit bigger. And this is the problem of a MI score, and this is the problem of the threshold, that we can set a higher threshold, for example 20 or 50, but the threshold is a count, so it is not scalable. So if we somehow fine-tune the MI score that the threshold of 50 is good and we have good results, but for much bigger corpus we have quite different results, because the threshold is actually different. So to use these thresholds, we have to use the relative frequency, This is the example of Rook Dice, which is my preferred score for collocations and so on, which is based on relative frequency, and so it scales very well. So the numbers we are getting from different sizes are quite the same. There is a built-in threshold that if the log dice is positive, there is a threshold that the relative frequency of both parts of the collocation are 1 to 64,000. So and this threshold is based on relative frequency. So the log dice is scalable and works very well. Okay, and about word embeddings. Word embeddings are the, say, numeric representation of words or any items we say somehow for which we compute these embeddings. So we are embedding the words into vectors of numbers, and there are many methods how to compute word embeddings. It started with word2vec, and there are say more advanced or a bit different methods like fasttext and glove, and in the last few years the context vectors based on BERT or other modifications. And the main message is that all these methods are not scalable. There are many not scaling parameters like a number of epochs, different initializations, different learning rates, and all these are some magic numbers which are not scalable. So in the results, the embedding stability is quite low. For example, when we run several times the same algorithm with the same input, because of the random initialization, we get different results, which is expected, but the quality of the vectors are different. We have different similarities of words or of the vectors of words, and when we make the computation longer from the same initialization, so we have the very same start, we run the algorithm, stop it, then save the results, and then continue with the learning. We also get different similarity values. So there is usually not so big differences in say list of nearest neighbors. So we get the same list of or similar list of nearest neighbors for some words, but the numbers of similarity is different. And so using these numbers in some applications or in some algorithms can give us different results. And of course, for different corpus, we have different similarities. So the stability is quite low, and sometimes it's worth to run the same algorithm many times and choose the best result out of several random runs. Yeah. Okay, so this is the stability of embeddings, and now the conclusion. First, mind the scalability, because it is important, because we use very different numbers, very different counts, and we need scalable mathematics in processing natural language. The second is that counts are not scalable, and to use these counts, we have to normalize them to make them scalable. Third, log dice as a association score is scalable and works very well. And the last, that word embeddings are promising. I think that we will see much more applications of word embeddings and neural networks and similar methods in lexicography in the future. But the current techniques are not scalable, and we have to mind that it is not scalable and work around it somehow, or at least beware that it is not scalable. Okay, so that's all. Thank you.
Thank you very much, Pavel. Before we go to any questions that might appear in the chat, I would actually have one. So going back to the word embeddings, any ideas from your side how to solve the scalability?
Well, I think that we can find a method how to compute these word embeddings, which are not so sensitive to the random initialization, and that they give us the same numbers, so we can find probably scalable method of computing word embeddings, but they are not yet in the use.
Okay, so there are two questions in the chat. One is related to the embedding, so we'll start with that one. For which purposes would it be, from your perspective, necessary to have scalable word embeddings?
Well, I think that it is needed for any research, because we need repeatable results. And if we get different results for the same input, then it is hard to do any progress, because we do not know whether the improvement was just a random or it was caused by some improvement in an algorithm. So I think that for any research, the stability of results is crucial, and so we need stable word embeddings.
Okay. The other question relates to the count normalization. What would happen if we reduce the normalization denominator to hits per 1,000 instead of hits per million? Would this reduce the bias for small corpora?
Well, I think that it doesn't matter whether we normalize to 1 million or 1,000. It's just the interpretation of the number is different, but it doesn't matter which say constant we use.
Okay, thank you very much. Also for the excellent timing. We've about